Bismillahirrahmanirrahim. Assalamu alaikum ji. Today we will start with a new topic, neural networks. So neural networks is a term which is used as a buzzword these days. But in fact, they are much simpler than what people imagine. A neural network is nothing more than a bunch of neurons connected together. And it works similar to the human nervous system. So if I tell you that we have studied neural networks in this course earlier. Yes, we have studied perceptron, which was a model of neuron. Right? So a perceptron is a very simple neural network in which we take a weighted sum of the inputs and we pass the weighted sum through an activation function. And if an activation function is a step function, we call it a perceptron. And if we replace the step function with sigmoid, that is logistic regression. So we have studied neural networks before. So we'll start with the establishing connection with perceptron and logistic regression, and we'll give you an overview of neural networks. And then we will define the notation that can be used to relate input and output of neural network through the parameters that characterize the neural network. Then we will define what we call the forward pass, that is traversing the neural network in the forward direction, in the direction from input to output. And then we will talk about the role of activation functions in neural networks and what are the possible activation functions we have. And finally, we will conclude this topic that given neural network, how can we learn the parameters of a neural network using the training data? And we'll be studying this approach backpropagation method to learn these parameters. Right? Okay, let's begin. We start with our prior knowledge, that is establishing a connection with logistic regression and perceptron. So we have d number of real valued inputs and we have a Boolean output. And we studied a perceptron model, and that was we have inputs and we take a weighted combination of inputs and we add this bias term to it. So this is aggregation, and what we get is W transpose X plus B. And we refer to this as pre-activation output of perceptron. And then we pass this pre-activation output through this step function, which we call activation function. If W transpose X plus B is greater than or equal to 0, output of activation function is 1 or 0 otherwise, right? So it combines inputs by assigning different weights to each input. We add a bias term and we pass this weighted combination through activation function to obtain either 1 or 0. Okay, so this was perceptron model. And we have studied this in detail, that what's the decision boundary, how do we learn this how do we learn the parameters of perceptron, and so on and so forth. What was logistic regression? If we replace this activation function with a sigmoid function, this becomes logistic regression model. So instead of step function, here we have a sigmoid function or logistic function. And it is defined as 1 over 1 plus exponent raised to the power negative of this weighted combination, W transpose X plus B. So this is logistic regression model, also known as sigmoid neuron. So in perceptron, the activation function is a step function. In sigmoid neuron, so we replace activation function with sigmoid function. And if we compare the characteristics of perceptron versus sigmoid neuron, so in perceptron, we only have two outputs, either 0 or 1, right? And we have a sharp transition from 0 to 1. If weighted sum is greater than or equal to 0, 1, if less than 0, you get 0. But in sigmoid neuron, you can have any values between 0 and 1. So these are the two choices of activation function. We will look at more activation functions shortly. For now, we can say that activation function introduces non-linearity, because what we're getting is a weighted sum of input plus bias. So that is linear transformation. And after linear transformation, we pass this linear combination through activation function. So far, we know step function and sigmoid function or logistic function. So this activation function introduces non-linearity, right? If we generalize this and what we call a neuron model. So in neuron model, we say we have a weighted combination of inputs plus bias term. This is effectively the same, right? So here in this block, we have two operations, right? So first one is aggregation, and then we have this activation function G. So this G can be a step function, this G can be a sigmoid function, or it can be any other activation function that introduces non-linearity. Okay. So the perceptron is a model of biological neuron, and obviously it isn't a complete model for decision human making. Sigmoid neuron gives you flexibility, but in fact we can have any activation function here that maps a linear combination to some number or to the so it's a one-dimensional mapping from a number to some value through a step function or sigmoid function. And we will refer to this G as activation function, right? We can have a more compact representation. So we do not, if we don't use the weights here, we assume that the weights are inherently part of this block, right? So weight is a parameter. So this neuron has two parameters, weights, W1, W2, WD. So weight belongs to RD. And then we have a bias term, P, which is scalar, right? This is a neuron model which is characterized by weights, bias, and activation function. So weight is W, bias B. So there are model parameters. And activation function G is a hyperparameter because it characterizes the output of or the mapping from the weighted combination to the final output. So activation function G characterizes neuron and it's a hyperparameter. Whereas once you define what activation function you use, you can learn the weights and bias for a given data. And therefore weights and bias correspond to model parameters, the parameters of neuron. We used logistic regression and perceptrons for classification. And we saw that using these models, we could have a linear decision boundary in the feature space separating the classes. Obviously, we could have a nonlinear boundary if we apply some pre-processing on the features. But now it should seem plausible, and you should expect that if you have a complex network of perceptrons, you can make quite subtle decisions. We know that a single neuron can give you a linear boundary, but if we connect these blocks in a sequence, we could have a more complicated boundary. Let's look at one problem which we cannot handle using a single neuron. And in fact, this is the problem that was shown to be a limitation of the perceptron, and that is infamous exclusive OR problem. Right? So back in 1969, it was shown that a perceptron cannot classify XOR output. So this is XOR function for two binary inputs, Boolean inputs. You get 1 at the output when either of the input is 1. and you get 0 when both inputs are 1. So this is exclusive OR. If we see in the two-dimensional space, so for these 2 points, we have 1, and for blue points, we have associated label 0. Obviously, the classes are not linearly separable, and therefore we cannot use a linear classifier. We cannot use perceptron. So one possible solution could be we transform feature space, or we project data to a higher dimensional space to make the data linearly separable, to make these points linearly separable. Or alternatively, we can build a network of linear classifiers. We can build a network of perceptrons. Okay, the idea is if we learn and or boundaries, right? So this gray boundary is boundary of OR function, and this is and. Right? So and classify every point here as 1, every point here as 0. Similarly, OR function would give you 1 here and give you 0 here, right? If we learn these two classic boundaries and intelligently use these two boundaries to classify exclusive OR output, we can, right? Okay, let's see, how can we do this? So using 3 perceptrons, we can resolve the output of XOR. Right? So this is the AND boundary, right? The blue one, right? As I said earlier, blue gives you 1 here and 0 here. But here I have inverted the output of AND with -1. And with this inversion, right? So what we get 0 here, right? And 1 here. And this gray gives you 1 here and 0 here. And if you can combine these two, right? So we get 1 in this region. You get 0 here and you get 0 here. So this is network of perceptrons. We have connected perceptrons in layers. Output of one perceptron is being used as an input to other perceptron, right? So we can say this is my one layer, and once we get the output of these two perceptrons, we pass the output to another perceptron, to another neuron, to obtain the output. And in fact, this is a neural network. To be very precise, this is a network of perceptrons, which is also known as a multi-layer perceptron, right? So we have a multi-layer perceptron. This is one example, but in general, the neural network looks like this. So a set of neurons organized in layers. So we have 4 neurons. So in fact, 4 nodes feeding 3 sigmoid neurons or perceptrons or general neuron we have studied. And the output of these three neurons is fed to another neuron and to obtain the final output. The leftmost layer in this network is called the input layer. And the neurons within the input layer are called input neurons. The middle layer is called a hidden layer, since the neurons in this layer are neither inputs nor outputs. When you see the word hidden for the first time, it perhaps sounds a little mysterious, but it simply means neither input nor output. It's hidden layer. It's hidden from you. And finally, the output layer is known as the output layer, the last layer. Right? So each unit in the network is called a neuron, and the network of neurons is called neural network. How do you interpret this? So what's happening in each of these neurons? So it takes a weighted sum of inputs and it passes the weighted sum through an activation function. And what you obtain is a nonlinear mapping enabled by activation function. Okay, I can explain this way. Output is a nonlinear function of a linear combination of nonlinear functions of a linear combination of inputs. Okay, let me explain. So the output here is a nonlinear function because here we have an activation function G and here we have sigma. So it's a nonlinear function of linear combinations of nonlinear functions of the previous neurons of linear combination of inputs, right? Given the input and parameters of these neurons. Okay, if you connect, what are the parameters of a neuron? So for each neuron, we know we have weights and we have a bias term. The activation function is a hyperparameter, it's not a parameter. So given the definition of neuron, given the activation function, given input and parameters of neurons, we can determine the output by traversing neural network layer by layer. Right? And once we reach the output, and we can determine the output. And this traversing from left to right, from input to output, is referred to as what I've written here, forward pass. Right? So the design of the input and output layers of a neural network is often straightforward. There can be quite an art to the design of the hidden layers. In particular, it's not possible to sum up the design process for the hidden layers with a few simple rules of thumb. So instead, neural network researchers have developed many design heuristics for the hidden layers, which help people get the behavior they want out of their neural networks. For example, these heuristics can be used to help determine how to trade off the number of hidden layers against the training time. Right? The number of neurons should be used in each hidden layer versus training time, and so on and so forth. Right? But we will not focus on the design of neural networks, but rather we will focus on the analysis of neural networks. Given neural network, how do you get the output for a given input? Mathematically, how do we relate input and output? And for a given neural network, how do we learn the parameters? Right? Another example of neural network could be a 3-layer network, 2 hidden layers. And this looks like something like this. So we have input layer. So it's a 3-layer network. So but you can argue that there are 4 layers: input layer, 2 hidden layers, and output layer. We do not count input layer as a layer because they're inputs. So the 3-layer here means 2 hidden layers and 1 output layer. And you can interpret it as that output is a nonlinear function of a linear combination of nonlinear functions of linear combinations, and so on and so forth. And you can do this. Right? So you start from output. So it's a nonlinear function. So nonlinearity is here, right? Of linear combination. Sorry, the first output is nonlinearity is here, right? Because this is G and this is sigma, right? So a nonlinear function of linear combination of nonlinear functions of linear combinations of nonlinear functions of linear combination of inputs, right? I assume you got an idea. So as I said, we do not count the input layer because there are no parameters associated with it. So neural networks with neurons are also referred to as multi-layer perceptrons in the literature, but we will refer to the network, network as MLP only when it is constructed using perceptrons. I will correct this. So I'm going to define another term which we call feed-forward neural networks. So the network we have discussed here is a type of neural network which we call feed-forward neural network, because output from one layer is used as input to the next layer. There are no loops in the network. Information is always fed forward. It is never fed back. If we have a situation in which we have loops, we would end up with situations where the input to the sigmoid function depend on the output. And that would be hard to make sense, and therefore we don't allow such loops. There are models in which we allow feedback loops, and they are called recurrent neural networks. But in this course, we'll focus on feed-forward neural networks. Output from one layer serve as an input to the next layer, right? So I've given you an overview of neural networks. So before we study the notation, we can answer a very simple question. What kind of functions can be modeled by a neural network? If you recall the exclusive OR problem, we could separate the data that is not linearly separable using a neural network. What else we can do with neural networks? We look at one example in which we use Sigmoid Neuron. So we take two inputs, X and Y, feeding to a Sigmoid Neuron, where 0.5 is a bias term indicated here. And if we see this as X, Y, Z in a three-dimensional space, right? So bias is 0.5, weight for X is very large, and weight for Y is 0. Although we have used Sigmoid Neuron, but we have chosen a very large weight for X, and therefore we get a sharp step-like transition along X. We do not have any transition along Y because the weight for Y is equal to 0. Right? So you get 0 for these values of X, you get 1 as an output for these values of X, almost 1. And this transition from 0 to 1 is very sharp because the weight for X is very large. Right. Similarly, if we choose very large weight for Y and 0 weight for X, we get a step-like transition along Y. This is what we can achieve using a single layer perceptron, or one perceptron or one neuron. We can have a decision boundary in a two-dimensional space that is linear. What we can achieve if we use two layers of perceptrons. Okay, let's look at, so we know that if we use two layers of perceptron, we can achieve something like this. Okay. So here I'm using X and Y, right? But so we're using, so this is being fed here, this is being fed here, right? If I assume that I'm not, the weight for Y is equal to 0, right? So I get, due to this 0.30, I get this transition along X, and for 0.70, I get similarly step-like transition, which is something like this. But when I combine these two, I have used minus 0.6 for the second one, and therefore consequently, we can have this pulse-like transition along X. Similarly, if we use 0 for X and use large value of weight for Y, I can get a pulse-like transition along Y. Okay. This is a two-layer network. This is also a two-layer network. This is also a two-layer network. How do you interpret this? So here, the input is only X. This is equivalent to 0 weight for Y. You get 0.4, 0.6, you get 0.30 and minus 0.20. You get a pulse-like transition along X. And this would give you a pulse-like transition along Y. And when you combine all of this, you get something like this. Right? This is high nonlinear. Right? So we have used step functions to have a three-dimensional bump function using a two-layer network. Right? Okay, so these are some of the graphical representation, but if we generalize this, and if we answer a question that what kind of functions can you model by neural network, so we just use a theorem, what we call universal approximation theorem, proposed by Hornig in 1991, and that is a single hidden layer neural network with a linear output unit can approximate any continuous function arbitrarily well, and given enough hidden units. So we can model, we can have any continuous function. So these results demonstrate the capability of a neural network. But obviously, this does not mean there is a learning algorithm that can find these parameter values. Since each neuron represents non-linearity, we can keep on increasing the number of neurons in the hidden layer to model the function. If you keep on increasing the number of neurons in the hidden layer, so we can model non-linearities. But this will also increase the number of parameters, the complexity of the model. In general, instead of adding more neurons in the same layer, we prefer to add more hidden layers, because each hidden layer means where we are, when you have two hidden layers, right? So you have a composition of non-linear projections, right? Because when you have one hidden layer, you have a non-linear output of linear combinations. But when you have two hidden layers, non-linear combination of linear combination of non-linear combinations, you have non-linear projections of a non-linear projection, and therefore you can model complex functions relatively easy. Right? So this concludes the overview of neural networks. So now we know what we mean by neural network and the capability of neural network. In the next video, we will define the notation, mathematical formulation that relates input to the output of a neural network given the parameters. Right? We stop here and we'll continue in the next video, inshallah. Allah Hafiz.